Okay. Hello, everyone. This is cs260, and we are on week 4 of this course. This week, we're going to focusing on sorting and recursive functions. These are important concepts for this course. So I'm hoping that I can give you some further explanation on those data structure and algorithms. So first, let's talk about recursion. What is a recursion or recursive function? So, you probably already know what function is in any programming languages. Basically, a block of code that can be reused by wrapping up, those code with a name and some parameters, and it will return some values. Typically, this is the definition of a function in computer science. Now, the recursive function basically is a function that can be calling itself again and again, right? So that's simplifies the term, but again, let me give you an example to illustrate this. Say, for example, a typical scenario is you are waiting in line, right? Let's simulate the line like you're waiting in a queue. And then you want to know, okay, you're waiting in queue, you have a bunch of person waiting in queue, these are persons. And this person, you're at the end of the queue, you want to know, what position you are in, like how many people are in front of you, right? So that you can estimate how long it's gonna take to check out something or do something. Okay, so you can ask the one in front of you, say, hey, which number are you, right? Which position are you in? Well, the people in front of you will not know his position, and he will ask again the people in front of him or her, and then this pattern continues. So all the people just ask one person in front of him or her until it reaches the last person, the first person in the line, in the queue. He don't have any person in front of him. He or she must know that he's number 1, right? Then he tell the person up behind him, say, hey, I'm number 1. Then the person immediately know that I'm number 2 because the person in front of me is number 1, and the person behind him says I'm number 3, and so forth, all the way back to you, and then you just add one to whatever the number reported from the people immediately in front of you. So that's kind of a recursive thinking, isn't it? All right. So let's implement this recursive function in code. Okay, so let me use the data structure that we just learned last week, which is a linked list, right? So let's simulate this as a linked list, and we're gonna implement a function called myPosition. myPosition in line, okay? You're waiting in line, and I'm gonna pass in the head of the linked list. So, and you want to know essentially how long is the linked list, right? Okay, so a recursive function has 2 essential elements. One is called the base case, where you're going to solve the problem in a trivial way. Like you can reduce the problem in a smaller problem, basically, and solve it. So the basic case is typically a trivial or simple case. So in that analogy, right, you're waiting in line. That trivial case is the person in the first. So the person in the first is there's nobody behind him. There's nobody in front of him. Then he knows he's number 1, right? We can make it even further. If there's nobody, right? So not had means it's null. Then we're gonna return 0, right? So nobody is there. Else, I'm gonna just add 1 to the position that is reported by the function. Right? I'm just calling this function again until I got the end of line. End of line means it's nothing, right? So what I pass here is, I'm calling the self, but again, when I call myself is current as head. So if I have anything after me, then my next pointer will point to the people in front of me, right? So I'm going to passing in my neighbor or my the people that in front of me. I'm asking, hey, what number are you? And he will in turn call the people in front of him until there's nobody in front of him, then that's 0. And the first person will get 1 plus 0 is 1. Second person will become 2 and 3, and so on. And at the end, it returns to you, and you will print those numbers. Okay, so let's test this out, where I can start a queue. Okay, can start a queue. Let's test this. Okay, the queue have 4, 2, 1, 3, those elements. Oops. And then I'm gonna print out the my position in the queue is, and then I'm gonna call my position in line, and passing the queue. Okay, and of course, end it. All right, let's run it. So, oops, there is found after. Yeah, forgot the semicolon. That's a typical errors, all right? All right, so my position queue is number 4 because I have a list of 4, 2, 1, and 3. So I'm number 4, 1, 2, 3, 4. Okay, so that's basically a simulation of a typical recursive function. It's very simple and straightforward. In our Xi books, we have another example to print the alphabet backwards, right? So to help you understand this function, so a function is basically when you're calling a function, okay, it's from another function like main function, right? You basically put everything, you save everything and then you go to that function on top of that. So it's basically like a stack of functions, right? So the newest function is always on the top and it has to be addressed first before you can address the function before that. So basically a recursive function basically is a calling function again and again and put those newer functions on top of the stack. Okay, so that in line very well with the stack ADT that you learned this week as well. So let's look at this function. What is doing? Well, it's printing the alphabet backwards, right? It printed the alphabet backwards by calling this function recursively again. Okay, so initially you start. Let's make an example with just the 4 letters, right? A, B, C, D. So I'm starting with D. Okay, and then I'm calling this function initially, passing the letter D. And what happens here is you can see you have a base case, right? This is a base case. The base case basically saying, hey, if I reach the letter A, I'm going to print this letter. Otherwise, I'm going to call in this function again, print the letter before me, right? You know, in C++, the alphabet is continuous, it's a number continuously in ASCII table. So if you -1, you get the letter before you, right? In a reverse order, okay, in the alphabet. So, but before you actually calling that function stack, you're gonna print out the current letter, then doing the function stack. So in the in the tech jargon, it's called the pre-order traversal. So basically, if you're doing pre-order traversal, you're gonna print the current one first, and then you're gonna call in that again, and then that's why you're doing this in a reverse order. So let's visualize it. By the way, PythonTutor.com is an awesome website that help you to visualize some of the key concepts in programming. It can simulate Python, C, C++, Java. So there's a lot of language you can do. Okay. So let's try see it. So initially you start with a function stack, main function. Starting letter is D. Right? Actually, after you execute this statement, the starting letter is D, and that's in the main stack, right? My function stack. Okay. So now you are calling this function again. You can see a new stack is created, although this is like the reverse. It should be on top, right? So imagine this is a new stack with a current letter D, and then because the base case is A, it's not the base case. It will go and print out the D first, and then go to another function stack. In this case, it will become C, and then it will call the print out C, go to the function stack again, and this time it will be B, right? The letter will be current letter will be B, and it will print out that, and then finally it reaches the base condition with current letter is A. It will print out this current letter and return. Once it's returned, nothing will, because this says nothing after. So the return point is at the green line, the line 11, right? After backwards alphabet, it will return, and the previous stack is going to be killed, and then you're going to reach the current stack B. And then because nothing after this thing, so there's nothing to do. It just simply return stack until it returns to the main stack. So it print out the ECPA. Now, what if I want to do this, right? What if I'm gonna modify this code? Basically, I'm gonna just say return. Okay, and then yeah, and okay, and then if I change this order, instead of print it before we do recursive call, we put it after we go recursive call. This is called post order traversal. So let's see if we do that, will that change my order, right? Well, to change my order. So let's see how it goes, visualize it. I'm just simply changing the location where I print the current letter. And let's see if that will change anything. Okay, so let's run it. So first of all, I'm going to the D, and we're not doing anything yet because we just keep calling this D, C, B, A. Right? And then I'm reaching the base case. I'm going to simply return it. Okay. And then I'm going to print out the current letter, B. Okay, so let's just edit this code. I didn't print out A because A is in the base case. And once you return it, the current letter is becoming B. The stack A is gone. So I have to modify a little bit just to print out this again. Okay. All right, so this will be good. And then visualize again. Hold on a second. Yeah, I have to be compiled, so that's why C++ is slower than Python. Python is an interpreted language. It won't require a compilation, so it's run much faster on the web browser. Okay, so let's try it again. So this time we're gonna do DCBA, and then we're gonna print A first, and then B first, and C first, and D last. Okay, so by just changing the order when before you enter the recursive call, after you enter the recursive call, you're changing the order that it was received. All right, so this is called the post order traversal in recursive call. All right, so now you understand a little bit about recursion. We can talk about sorting using recursive function calls. Okay, sorting using recursive function calls. All right, let's still keep this node because we're going to use that later, right? So there's two different remember we have a pre-order traversal and post-order traversal. That actually corresponding to these two similar but different concept, recursive sorting algorithm. One is called quicksort, one is called merge sort. Okay, quicksort is like pre-order traversal. It does the partitioning or work first before it enters the recursive function calls. And merge sort is the opposite. It do the recursive function call first, and at the base case, when you return, then you do some merge actions. So that's the key difference between these two. All right. So let's talk about quicksort first, which is the pre-order traversal recursion functions. So the idea behind a quicksort, right, lies in the fact that let's define a function prototype. So quick sort. So given a num array and also let's say I is the initial index and k is the last index, right? I want you to sort this array using recursive function call. So basically that means I'm gonna call itself, right? So basically the idea of quicksort is if I can pick a pivot number in a list, right? For example, if I have, I don't know, let's define a main function first. So we can have some test case, right? Okay, so test case, if I have numbers equal to, array of numbers equal to, let's say 10, 2, 78, 4, 45, 32, 7, 11. Okay, so that's our test data, right? And of course, we're gonna also specify the size is, of course, there's 8 element in, and then we gonna start always with 0, right? Starting point, and I'm gonna print it origin array. We're gonna print out this array, right? For I. Okay, I'm going to print out the number. Okay, and then finally, new lines, right? Okay, and then we're going to call the quicksort with number 0 to size -1, well, -1 because we're starting with 0 index, right? And then we're gonna do that again with the print function. Well, actually, let me just define a print function. Okay. So I don't need to, print array with int num. Okay. And then I'm going to put this here. Cut, paste. All right, so that's the call print array is num. Okay, And then after that, we're going to print again. Okay. All right, so we set everything up. And I'm going to say sort it. Okay. Quicksort. So first of all, I'm gonna, just return. I do nothing, and I'm gonna run it. Hopefully there's no error. Oh, there's count of them. Yes, std and l. Run again, and where is the standard cout? Oh, here. That's why you use namespace everywhere, right? And sorted array. Come on. Put it in the wrong place. Use the wrong ticker identifier. Oh, okay. Wait. What's going on? Oh, there's a size. Yeah, of course. Int size. So I have to give them a size of size. The size. And of course, I have to define int. Okay. Okay, here you go. Original array 10 to and sorted, because we haven't sorted yet, right? So just a test. Okay, so now Quicksort. How do I do the Quicksort? Again, the idea, the base framework is that we're going to divide this number into half, right? But I'm going to pick a pivot point. There's multiple ways of pick a pivot point. You can pick the first number in the array, or last number in the array, or middle number in the array, or sometimes you can randomize a pivot point in the array. All these things are just make sure you can avoid the worst case scenario where the number is already sorted. And if you are having to pick the worst case, then the order of complexity will be O of n, right? Because you just n squared basically. But then if you do it correctly, then it could be n log n algorithm. All right. So basically, you partition this. Every time you do partition, you will get a int pi, partition index is 0. And I'm going to say every time you get partition index, it will be partition. Okay, there's another function called partition with numbers and I and k. Okay, so every time you get a partition index, and then you can divide it into two parts. So quicksort recursively, numbers from I to pi, right? That's one, and then quicksort numbers from j plus 1 to k. I'm sorry, not k, the pi, right? The partition index plus 1 to k. So you divide this into two. Remember, this is a pre-ordered traversal in recursive function. So that means you do most of the work at the current node, current situation, current function stack, and then you pass along to recursively call these two subarrays, right? So you basically, every time you do a partition in one function, the position of that number in the final sorted array is determined. So every time you do this pre-order, you just determines the position one at a time. But then you're doing this recursively, so hopefully you can actually you're doing it pretty quick. So what is this function called partition? Oh, we haven't defined the base case yet. Otherwise, this will never stop, right? So what is the base case here? Sorry, for the quicksort. That's important. What is the base case? The base case for the quicksort is if there are 1 or 0 elements to sort. Because if you have 0 elements or 1 elements, then obviously you don't need to sort, right? It's already sorted. So that means if the index I is greater or equal to k, so starting equal to the end or starting is exceeding the end, then I'm gonna return. Just simply return. So there's nothing to do, right? Otherwise, I will just keep partitioning. So you can see most of the heavy lifting is in the partition part. So let's look at the partition. But overall, this code is pretty simple. Usually recursive functions are pretty simple in writing, but it's not simple if you think about recursively, right? Some of you may have seen a movie, Inception, where in the movie, the story is that you're in like 7 level, couple level of dreams. So you're dreaming inside your dreams, right? So this is similar to the recursive call. You are calling function inside the function until you reach the base case where you're going to return, right? Otherwise, you can't not wake up forever. So what is this partition doing? Okay, so let's define a partition function. This partition function, okay, take array and the boundary, the starting index and the end index. Okay, so let's pick up the middle point. First of all, this is our pivot point. Middle point is equal to I plus k minus I divided by 2. Okay, there is a little trick when I already told you in binary search. If you write this way, it will overcome the integer overflow, potential integer overflow problem. And then pivot number is basically num of that index. Okay, so you got the pivot in the middle. Oops, there's a typo. Okay, you get the index and the pivot number. Now, okay, so let's use this example, right? Let's use this example. So you pick pivot font one. So maybe you pick the number 4 as a pivot point. All right. So what I'm gonna do is I'm gonna use 2 pointers, a left pointer, and then right pointer. Initially is initial left equal to I, right equal to k, right? I and k is the initial left boundary and right boundary of this number array. Okay, I'm gonna using the left and the right because we're gonna actually move the left to the right and move the right to the left, and they are approaching the middle. Okay, we're doing this 2 pointer stuff. Okay, and I'm running a while loop, right? I'm gonna have a Boolean value done is false to start with. Well, not done, right? So we're gonna keep increment L. of left if that's less than the pivot, right? So the idea is if the number is so we want to basically rearrange this list such that all numbers less than the pivot will be on the left, all numbers greater than the pivot will be on the right. If you do that, then you can finally sort the left half and the right half, right? As long as the left half and the right half are in order, the whole array is in order, isn't it? Because you know that nobody at the end of this partition, all the numbers that's so I'm in a pivot number, all the numbers that's on the right side is greater than me, all the numbers on the left side is less than me. So if they are itself sorted, then I'm guaranteed that the whole list is sorted, isn't it? Okay. So, but if there happens there's a number that's less than me, less than the pivot number on the left. If that's the case, then it's normal, right? We can just increment increment the left. Now, of course, we can put in the body of this. Okay, let's do that. Make it clear. So we're gonna add the left, right? And then if number of right is let's say number of right is greater than pivot, right? That should be the case. I'm gonna decrement the right, okay? So after this two while loop, I'm guaranteed I have a left pointer that points to the number that need to be thrown across the pivot point to the right. And I also have a number on the right side that's less than the pivot and need to be fixed or thrown into the left. So these two positions need to exchange, right? These two positions need to change. But if we're lucky, right? If all numbers are already sorted, then I don't need to exchange anything. So in that case, if the left pointer is greater or equal to the right pointer, okay? If that's the case, that means I went through all the numbers and nobody, they're all in place. In place means all the numbers on the left pivot is smaller than pivot. All the numbers on the right pivot is greater than the pivot. Then I'm gonna update down equal to true. So next time it will go outside the loop. Else then that means we're gonna swap. Okay, we're gonna swap the numbers. So we're gonna swap, we use a temp to store the number left, and then number left is equal to assign number right to the left, and then number right is the original value of left, so it's 10. Okay, so we can swap it, and we already swapped it. And then don't forget, at the end, we're gonna add left again, and also add, decrement the right. Because after you exchange them, there may be more number that are out of place. You need to continue until you meet in the middle, right? Until you meet in the middle or cross the boundary, left is greater or equal to right. Okay, so that's the key of the partitioning. And don't forget, at the end of the while loop, once you're done everything like this, you're gonna return some value. What do you return? Think about it. After all this, right? Left the down is left is greater or equal to right. So at least the left is equal to right. So you can return the right. Okay, so basically that's the position that's what beyond the left partition, which is my pivot point. Okay. So this algorithm is using the middle point as a pivot point. You can also use the last point as pivot point, so you can just do all the exchange for the rest of the numbers, not including last, or pick the first one, the pivot, and using the rest of them, right? The idea is after this, you're gonna find a right location for the pivot number. So at the end of the sort, the pivot number is in the right position, but not the other. The other may still out of position. We don't know yet, but we have one guarantee: is every time you partition it, the pivot will be in the right place. Okay, so in this case, we keep it in the middle and we keep the pivot in the right place, and we just move around everything, near them, so that the pivot won't be needed to change again. So that's the invariant of this partition. Okay, so let's run it. Oh, pivot, undeclared pivot. Yeah, I have to do it. Temp, of course, I need to declare temp. Yeah. And then K. Okay. 29. 51. Yeah, missing a semicolon. All right. Okay, so original array is 10, 2, 7, 4. That. Quicksort, size -1. And didn't print sorted. I think there's something wrong with the with this. Okay. Oh, okay. This one should be inside this else statement, because when you're done exchanging, you have to move on, right? And I guess that's it. Let's check. Right is greater than pivot. It's minus right. Left add members. Left is less than pivot, and numbers pivot. Okay, plus K minus I divided by 2. Okay. I guess that's pretty cool. Let's run it again. Yeah, okay, that works. So you can see original array is 10, 2, and sorted is 2, 4, 7. Okay, so that's the one major recursive function algorithm is called Quicksort. Quicksort is used very often in sorting routine. In a lot of libraries or language like Python, it's already incorporated into a function, so you can just use it, but you can at least know where it comes from. Okay, so that's Quicksort. How about merge sort? Well, you already have some experience with merge sort in the Zai books. Basically, it's it's a post-order traversal of a recursive functions. So you, instead of doing some work before the recursive call, your recursive call, it divide the array into 2 parts. Okay, and you divide the array into 2 parts until you get like if you have n elements, you get n array of single elements, and then after that you get to the base case, which you get a n number of 1 single element arrays. You're gonna merge them, right? So at the bottom line, you have 2 single element array. It's very easy to merge them, right? You can just put them in order, and then you can merge the other 2 and the other 2, and then finally you go level by level. At the top, you already merged everything. So it's also a similar to Quicksort, but it's a post-order traversal. So let's implement this Quicksort. Merge sort. Now, in this case, I'm going to provide you a question that's different than what's in the Zybox. The Zybox, they're using a regular array, right? Because you can quickly go and find the middle array in the array, middle element in the array. But this time, I'm going to ask you to sort a linked list. Okay, so I'm going to give you the header linked list to return the list up sorting in ascending order. Okay, so there's a couple of challenges in a linked list, but we'll see. Okay, let's code the solution of linked list version. Okay, so the solution for sorting a linked list using merge sort. Okay, so let's see how can you do that in the merge sort. So I'm going to define a couple of functions. First of all, the framework for the merge sort, okay, is pretty straightforward. So list node merge sort. Okay, merge sort. I'm providing a list. As you can see, the only thing you need to provide for the linked list is just the list head. And so what's it's a recursive function call, of course. What's my base case here? Well, with base case, if it's a null or single element list, right? Then you already reached the base case. Oh, there's a little trick. Sometimes you're missing the equal sign. You just missed 1 equal, then it becomes assignment, right? It will give you a lot of headache. If you keep the number on the left and the variable on the right, then the compiler will be your friend. It will remind you if you have missed this equal sign. Okay, so using this way, it's better. So if the single element, that means its next is no pointer, or its itself is no pointer, then I'm going to return what? Return head, right? Just return 1 single element, or head is null, then return null. That's the base case. Otherwise, I'm going to split lists into 2 parts. Okay, so the first part is my left side. I'm going to have a new pointer left to the head. Okay, I need to put in 2 parts, so I'm going to roughly divide in the middle. So I need to, in the array, you just quickly go to the middle, but in the linked list, you have to use a helper function to get you to the middle of the element. So I'm calling it get mid function. Okay, we're going to implement this function. And then, of course, the end of the node is the right side. It's the one next to the middle, right? It's your beginning of the right side. So now, after that, you need to divide in 2 lists. So the way you do it is in the middle will become the new end for the left side of the list. So the middle, the next is the no pointer. By doing that, and the middle next original point to the right, right, the right, beginning of the next part, second part. But then I'm going to cut it off by assigning to no pointer. So now you have two lists. One is the left, one is the right. So the left is, I'm going to merge sort, right? Merge sort again, the left. Okay. So I'm going to merge sort the left linked list. And the right is, of course, merge sort. Let me see if I spelled it. Yeah, merge sort right. Okay, so the right points to the beginning of the right side linked list. The left points to the beginning of the left side linked list. So essentially divide this into half. Okay. Then other than these details, it's very similar to the one implemented in the textbook, right, in the array. And then finally, it's post all the traversal. That means I'm going to do most of the work after we're going to merge the left half, the linked list, and right half. By that time, it's already left and right itself is already sorted. You can just merge it. Okay, so that's the difference between merge sort and quicksort. Quicksort is doing things before the recursive call, right? Doing partition, and merge is doing things after recursive call, which is doing the merge. Okay, so now we're going to implement these two functions. One is called the get mid, right? Using this node. Actually, this is list node. And again, get to the middle of the node. And then another function is called merge. Okay, merge to linked list. Merge list node left and list node right. So merge two linked lists into one list. Okay, so how do we implement the get middle? Well, you have a linked list, right? 1, 2, 3. 1, 2, 3, 4, 5. Okay, etc. How do you get to the middle? Well, somebody will say, okay, I will have to go through this list once, so I get the length of the list, and I go through it again. This time, just to go, say the length is 6, and going to 3 steps to get to the middle. Well, that's fine, but you're gonna go to the list twice, and it's order of algorithm, right? Okay, but then how can you do it without going to the list twice? Well, let's see. We can send 2 animals, right? One is a turtle, one is a hare. So let's let them race. So the hare runs faster than the turtle. The hare runs 2 steps at a time, okay? The turtle runs 1 step at a time. By the time hare reaches the end, where's the turtle? Well, it's in the middle, okay? So that's how you are gonna implement this in the middle. So let's see, this node, I'm define a slow pointer, which is here, how fast. I'm actually let the fast equal to the head next, okay? So if there is a fast node, because it's not node, right? So because if fast is no, that means there's only one element, and I just return that element, and fast next. So next is also not no, because I'm going to jump twice, 2 steps for the fast. For the slow, it's just jump once, right? Slow next. It goes to the next, one at a time. But the fast is going to jump twice. So the fast next. That's why we have to check if the next is not no. Otherwise, this one will have fragmentation fault. Okay. At the end of that, the hair reaches the end, but the slow or turtle is in the middle. That's how you get the middle. All right. So that's a very cool technique to get the middle of the element from the linked list, single linked list, with only one iteration. You don't need to do that twice. Okay, so that's a small trick. Nonetheless, we need this for the linked list, but we don't need this for the array, because array is continuous in memory. You can just get indices divided by 2, the last, first plus last divided by 2. Okay, so how about the merge? How to merge 2 linked list? Okay. Well, let's still using this example, right? So suppose you have 2 linked lists. 2 linked lists, right? 1, 2, 3, and 4, 5. Okay. Well, let's just do 1, 4, 3, 3, 5. 1, 3, 5. 1, 4, 2, and 3, 5. So how to merge those 2 linked lists? Well, you're going to compare the first element for the 2 list. Which one is smaller? We're going to get to that new list, 1. And then you move to the next. After 1, this becomes 4, 2, right? And then you compare these 2, and the 3 this time is smaller. Every time you just only pick the smallest of the 2 linked list, right? You only look at the head, and then next time it becomes 5. So you only pick the smallest of the list node. So this one is gone, and then 2. Oh, sorry. Yeah, I think this is not sorted. So this should be 2, 3, I'm sorry. And then 4, and then 5. Okay. So 4 is sorted. All right. So to translate that into code, I'm going to have a little trick and create a dummy node. Which points to the head. So I'm going to remember, actually, I'm going to create a new dummy node. Okay. And then I'm going to have a tail node. I'll tell you how to use this later, in a moment. While we have left list and right list. So they're not null. That means we're not at any end of list. So that means there's numbers in each list, right? So if that's the case, let's compare the list value. If the left value is less than the right value, what do you do? This is just one common case, right? If then the smaller value wins because it's ascending order. So I'm gonna send a tail next to the left, okay? And then increment left. So I'm gonna move the left. Okay. So the same thing happens to the right, right? So I'm gonna copy and paste. If the right value is less than the left value, which I can just capitalize it as else, right? If that's the case, then tail next is the right. And then we're gonna move right to the next. Okay, every time I pick one from a list, I'm going to increment that list point header so that head points to the next element. So every time you can just compare the head of each list, linked list. And at the end, if you don't, for any cases, we have to move the tail to the next, because every time you go through this, you will actually add one number to that new list. Okay. At the end, if it's not over yet, if left, you still have something left, pun intended, then I'm gonna put everything, append everything to the end of the list. Why I can do that? Because left is already sorted, so I don't need to worry about that, right? Else, if right is not empty, if right is not empty, that means I can do the same thing, put the next pointer points to the right, okay? So that the rest of them are already sorted is appended to the entire list. And what I'm gonna return? I'm gonna return, remember the dummy, because the tail starting with the dummy, but the tail is used to iterate through the list. At the end, the tail is the end. That's why it's called tail. But I want to return the head, right? So the dummy is next, is pointing to the head, the new head. All right. So at the end, this is a merged list. So as long as these two are sorted, this one will do it, no problem. Okay, so let's test it. But before I test it, I have to define a print list function. I'm gonna just paste it here because it's not as important, but you may have to think about how to print a linked list. Okay. All right. Okie doke. So everything is okay. I'm gonna test it in the main function. So I'm gonna do this. Main function. After this, I have this. All right. So two lists, and then solution. Okay. So I'm going to sort the list and print an answer, sort the list, print the answer, sort the list, print answer, run it. Oh, do I have a sort list? Okay. So I call it sort list. Actually, it's called merge sort. Okay. And this is the merge sort. Okay. And merge sort private member. Right. Oh, I see. Yeah, it's where's my class? So I have to put the entire thing into public domain, right? So now everything can use it. Till next. Again, did I miss the semicolon somewhere? Yeah, here. Okay, anything else? Is something kind of like print list. Yeah, it is declared. I don't know. Ooh. Print list. Okay. Oh, mid next. It's in 75. Yeah, all these semicolons. Keep hitting it. So I'm declaring my print list. If I can do that. Well, I'm gonna put the print list outside the solution because that doesn't make sense to. It doesn't necessarily need to be related to here, right? So I'm just put it here and call it a day. Okay. Here, I'm gonna just do the print list. Yeah, that's what I'm intended to do. Okay, here you go. Finally, original array, sorted array, 1, 2, 3, 4, -1, 0. That's the sorted, right? And then if I pass in a new pointer, it give me the empty array. All right. So here you go. I think you know, in this lesson, hopefully you learned what recursion is, very important. And recursion is basically calling the function stack again and again. And you need the base case to avoid the infinite loop. And then think about base case with pre-order and post-order traversal problem. And if you can practice this visualization in the pythontutor.com, that will help you understand some of these details. So I'm gonna rename this to, let's see, sorting. And then I'm gonna share this with you after the class. All right, that's all for today. Thank you very much. Bye.